It's a pleasure for me to now introduce to you a little bit what we are doing here in Equality Work Package 4, atomistic modeling of electrode materials for battery and fuel cell applications. This use case, this part is structured in two cases. The first one is material discovery for battery design. And here, as an introduction and motivation, I want to show that we are focusing on lithium-sulfur batteries. The basic working principle of such a battery is shown here on the right. You have a sulfur cathode and a anode containing lithium. And during discharge, the sulfur reacts with lithium, forming at the as an end product Li2S. And in the charging process, this goes the other way around. And of course, electrons are flowing back and forth and driving a certain load. So now, what are the advantages of lithium-sulfur batteries as compared to the traditional lithium-ion batteries? It's energy density. Both the gravimetric energy density measured in watt hours per kilogram and also the volumetric energy in energy per volume is much higher as compared to the traditional lithium-ion batteries. Of course, there are also some disadvantages. The current lithium-sulfur batteries have low life cycles, poor conductivity, and also a stronger volume expansion during discharge. And these disadvantages are the motivation for our work to do some basic research into the fundamental understanding of how a lithium-sulfur battery works. So we have mainly two objectives here. The first one is to develop reference data for quantum computer simulations using classical quantum chemistry and classical high-performance computers. I have to say there are no quantum computer results for this complicated case of atomistic battery and fuel cell modeling yet, but still our results and our calculations work as benchmark data for future quantum computer calculations. And second, we analyze in detail electrochemical reactions at the cathode in such a system. Key results and activities are a theoretical evaluation of lithium-sulfur batteries, revealing higher energy densities than traditional lithium-ion batteries. So we could reproduce what is known experimentally here. We could show that traditional density functional theory calculations with molecular models of the sulfur electrode fail to match experimental voltage profiles, and therefore we developed a hybrid Monte Carlo molecular dynamics simulation approach to successfully simulate this voltage profile. So how does it work? The voltage depends on the chemical potentials of the anode and the cathode, which then again depend on the chemical potential of the materials that are in these electrodes. A simple DFT calculation reveals that the maximum voltage is about 2.4 volts, while the literature value is very close to this. So we could reproduce the mass energy density and also the volumetric energy density of lithium-sulfur batteries very precisely, and also compare this to what is known for lithium-ion batteries. Here is again a sketch of the working principle of such a battery. Here you have the sulfur cathode, the lithium anode, and this sulfur cathode is at the beginning, before discharge, completely made out of sulfur. This is present in the state of such sulfur rings, ring-shaped molecules. And finally, it's transformed to lithium Li2S, which is a bulk crystalline material in ideality. So in order, what is experimentally known or very important is here the charge and discharge profile. This is the potential or the voltage of the battery or of the fuel cell of the battery as a function of its capacity. And focusing on the discharge profile here, this curve is what we wanted to model. So the shape of the curve is determined by the change of the anode from pure sulfur going through various intermediates down to pure Li2S. So in order to do so, one approach would be to use density functional theory to compute the energetics of directions from S8 over all these intermediate steps down to Li2S. So, and this could be done with a molecular approach by treating these species as molecules. But however, this failed. So, because in reality, the Li2S system and all the intermediates are amorphous. So the molecular approach misses a lot of interactions between the inside of the material. So we developed such an approach, which I will not explain in detail. However, it is possible to create these more or less random amorphous structures of all these materials that are converting from one to each other during the discharge. So, and here a comparison between the two approaches. Here, the molecular approach, we see that the potential or the discharge profile is as here. And if we use our novel approach, then we find a curve like that. And if you compare this last curve with the experimentally known red one, you see a quite reasonable agreement, much better than what is shown here. So in conclusion, the molecular DFT approach overlooks most of the intermolecular interactions, while our hybrid Monte Carlo MD simulations were developed to successfully predict the discharge profile. So the main thing here is that the lithiation and delithiation of the sulfur electrode leads to amorphization, and this is only possible. It's not possible to describe this with simple molecules. So this was a little bit short. Now to the more extensive case 2, our work on atomistic models for fuel cell simulations. Again here, as a short introduction, the system that we are looking at, a solid oxide fuel cell is composed of a cathode, where an oxygen reduction reaction occurs. In between is a solid electrolyte, and down there on the other side is an anode, where a hydrogen oxidation reaction occurs. These cathode and anode and electrolyte in between are all solids, while the cathode and the anode are not completely filled. They are like a sintered material composed of complicated ceramic materials that are necessary for transporting the oxygen ions and also the electrons. On the anode side, there is the same basic material as on the cathode, but it's mixed with nickel. So what are the advantages of solid oxide fuel cell? First, it has a very high efficiency. It is flexible in fuel use. You can not only use hydrogen, but could also, for example, use methane to produce energy, and it has very low emissions. A disadvantages of solid oxide fuel cell is that it has a very high operating temperature is needed for them, because the transport of oxygen ions is very slow. This can be shown on the top in this very extensive review paper, where they compare various kinds of different solid oxide fuel cells. And you see that for low temperatures, the peak power density is very low, and only at very high temperatures you get a reasonable power out of a solid oxide fuel cell. Also, another disadvantage is that quite a large size is needed for such a device to have a reasonable power density. Okay, here in this case, we had several objectives, or we put ourselves several objectives. First was to study the hydrogen oxidation at the anode using atomistic simulations, and also the oxygen reduction reaction at the cathode. Then to investigate the transport mechanism of oxygen ions in the interface between anode and between cathode and electrolyte, and also to consider some more effects on the cathode in operation condition. And key results and activities were that the water formation and adsorption on the nickel YSC anode is endothermic, presenting a significant thermodynamic barrier. Oxygen prefers to adsorb on the defective surface of LSC, of the LSC cathode. and is transported mainly through vacancies into the bulk. A Barter charge analysis revealed that the reduction of oxygen revealed the reduction of oxygen upon adsorption on the LSC cathode, and magnetic states and doping effects were studied in detail. Their effects were studied in detail on the vacancies of an LSC cathode material. So let's start with the schematic of electrochemical reactions on the solid oxide fuel cell electrodes. So when oxygen adsorbs on the there is the hydrogen and methane oxidation on the anode is possible, and oxygen reduction at the cathode. These are the two main things. So, and then there is the transport of oxygen ions in the electrolyte. So you see here, oxygen comes to the cathode, it adsorbs, and there are two mechanisms how it is transported through the cathode and through the electrolyte. Mechanism one is surface diffusion. So the oxygen adsorbs, it dissociates into two oxygen atoms, and the oxygen ions diffuse across the cathode to the electrolyte. The second mechanism is bulk transport, where the oxygen adsorbs again and then dissociates on defective sides of the surface, and oxygen ions are transported from the surface to the bulk via vacancies, through vacancies in this solid material. Yeah, atomistic models for fuel cell simulations. I will not say too much about this. Here we studied two systems. One is the pure nickel system, where water can adsorb, and the other one is a very complicated system that is more closer to reality, where we have here the YSC material and on top a piece of nickel. And this forms a so-called triple phase boundary, where the nickel touches the YSC material and the vacuum. And with this model, we could find a new reaction path. Water can be absorbed on the nickel surface and on the thing by forming nickel oxygen bonds. And this was only visible in this complicated triple phase boundary model. Coming now to the adsorption and dissociation of oxygen on solid oxide fuel cell cathodes and the detailed energetics of this system. Here we see that the first step is the adsorption of the oxygen on the surface with a certain adsorption energy. Then it dissociates with a certain dissociation energy, and further on it diffuses. And these energies we found out by doing this using detailed atomistic models. Yeah, and we compared this to the case. Here's the case where we have a clean surface, and here in this case the oxygen adsorbs on a defective surface. So in this case the adsorption energy already is different, and then when the oxygen splits, one of the oxygen atom keeps diffusing on the surface, and another one is possible to then diffuse into the bulk via defects. So from one defect to the other. And we did a detailed energetic analysis of this process and found out that as adsorption and dissociation of oxygen are thermodynamically preferred. So this process works. Now towards diffusion and migration of oxygen ions. What we have shown here is the adsorption energy of this of oxygen ions on various sides of the surface, and also the barrier for diffusion from one of those sides to one of those sides. And on the right side for the defective surface, we show here how oxygen ions can move from one defect to another. If you compare the position of the defect moves, and this is like in electronics a movement of a hole. So when the defect moves, another atom moves also, and this is then defect diffusion of oxygen atoms. And here you see the energy barriers going from one of these models to the other and back. So the critical diffusion barrier of oxygen atoms is lower on the bulk than on the surface. This is the main takeaway message of this. So now coming to now one further thing about atomistic models of fuel cells is effects, some delicate effects of distortion and also magnetism in the LSC cathode material. So traditionally, this LSC is such a bulk material, but it is known that in this bulk there are distortions possible. So comparing this to this, the energy of such a distorted system is a little bit lower. So if you plot this, focusing on maybe the red color alone, you see that the ordered system, the energy is higher, and there are two possible distortions where the system has a lower energy, and in reality, the system constantly fluctuates between this, and this state. And another thing is that in such a system, it's magnetic. So there are two possible extreme states. Here on the left, the ferromagnetic state is shown. So all spins point towards one direction. And the other extreme is the paramagnetic state, where 50% of the spins point in one direction and the other 50% in the opposite direction. And you see the paramagnetic state shown here in green. It has also the same order disorder effect, but in general, the difference between ordered and disordered energies in the paramagnetic states are lower, and also the minimum energy of the disordered systems is higher compared to the ferromagnetic state. So now our main goal was to study if we can change the material by doping. That is doping with 3D transition metal elements, namely manganese, iron, nickel, and copper. So 3D transition metal elements. This is. We do this by doping 1/8 of the formula unit on the B sides. That is, we remove one cobalt atom here and replace it with one of the doping elements. And also study how the effect of different magnetic states on these doped systems. So by looking at the doping energy for the different elements, we see there is a trend. So going from manganese to copper. And the doping energies in the paramagnetic states exhibit a slight reduction, so all the blue balls are a little bit lower than the red ones. But in general, the take-home message from this picture is here: doping energy means that here the system is more stable than here, so the stability decreases in this direction. So it would be in some applications better to dope with manganese than with copper, because this system is more stable and also especially more stable at high temperatures. Now we consider the effect of two different oxygen vacancy sites in the doping model. So oxygen vacancy means that we have an oxygen missing. Or the oxygen vacancy is when an oxygen is missing, and the oxygen vacancy formation energy is the energy that is needed to remove such an oxygen. And we study now how this changes when we dope the system with different elements. So this doping can occur here in the nearest neighbor site, that is, the doping element is close to the vacancy, or in the next nearest neighbor site where the doping element is a little bit further away from the vacancy. Yeah, and here again, for the ferromagnetic and the paramagnetic state, we show the oxygen vacancy formation energy as a function of the doping element, and we see some trends here. And these trends are different, are somewhat different compared to the undoped system. So the undoped system is always in the middle, the cobalt, and for example, going. So in the ferromagnetic and the paramagnetic state affect the oxygen vacancy formation energy in different ways. Okay, and now coming to the final thing, what we also did is a very detailed analysis of the electronic structure of the LSC system with doping. So what is shown here is the density of states for such a system. The Fermi energy is here, and this shows it for all the different doping elements. So the exact shape of these curves is not so interesting, but what can be seen is here is the ferromagnetic state, and here the paramagnetic. In the paramagnetic, the upspin density of states are nearly the same as the downspin. So these two bunches of curves are quite symmetric. And here in the ferromagnetic state, you see that the upspin density of states is always higher. So this proves that we are here in the ferromagnetic state. And then what we can do is we can calculate what is the so-called band center energy. And they exhibit modifications that are dopant and magnetic state dependent. The qualitative energy landscape remains consistent across all dopants, but the band centers shift in different ways. So these band centers are marked here in red and blue. Red is for the oxygen 2p orbitals, and blue is for the transition metal 3d orbitals. And these two are the ones that are mainly responsible for forming the chemical bonds in the crystal. So, and if you look at, they are all changing a little bit in position, and also the energetic difference between the two lines changes. And this is different in the ferromagnetic and in the paramagnetic state. So now, bringing this all together, the magnetic states both shift the oxygen vacancy formation energies and also the band centers. Different dopants result in different shifts. And interestingly, we found a linear relationship between the oxygen vacancy energy shift and the band center shift. So the band center shift is, or the oxygen vacancy energy formation shift is the difference between these energies in the ferromagnetic and paramagnetic state. And the band center, the band center shift is how these band centers move relative to the doping. And if you plot this all together, we find that these data points have a linear relationship, which is quite remarkable and interesting. Okay, the curious results of the whole thing is density functional calculations of molecular models fail to match experimental voltage profiles for the battery case, and so we developed a hybrid MCMD simulation approach to successfully predict the discharge voltage profiles. Key results for case 2 is that oxygen prefers to adsorb on defective LSC cathode surfaces and is transported through the bulk, mainly through the bulk via vacancy hopping. Magnetic states have a strong influence on oxygen vacancy formation energies of the doped LSC cathode, and element doping with 3D transition metal elements does not lead to a significant reduction in the vacancy formation energy. Sure. And with this, I'm at the end, and I'm happy to answer one or two questions if you like.